So thank you, everybody. Thank you for coming, and thank the organizer. I'd like to thank the organizers for giving me this opportunity to present some of the work that we do here in Oslo. Let me just do this. What I'll be presenting is some of the work that we're doing here. And you see our small team down there who have contributed to this particular work. So it's myself, and then Pascal Sado, and Hannes Nikisch and Wojciech Miloch. And so I thought I'd start with a bit of maybe a bit of personal background. So me and Hannes, we go on holiday every year with our families and other families as well. And one day we talk about what we actually do for a living, and Hannes tells me what he does. And so Hannes works at the Philips company, you know, the consumer electronics company, at the Medical Research Center in Hamburg in Germany. And they don't just, Philips, that is, they don't just build, you know, consumer electronics. They also build these big machines that are used in medical imaging. He has been in machine learning before machine learning was cool, or even, you know, it had this big renaissance, if you want, with some major advancements. And he's been in the business before, but at Philips, he's looking at these kinds of images as you see here. So I hope you can see that they're X-rays of hands. And really what he's developing is software which is internal to the imaging machine that helps the doctors make their decisions or their diagnosis. So it's anything from automatically calculating the volume of the liver, and for that you need to identify the liver in the image and then where the boundaries are and those kinds of things. So he has a background in digital image processing, and then particularly also machine learning. And when he told me that during our holiday, I thought, hang on a minute, I could use that expertise, because here's what me and Wojciech do. And I'll get to Pascal, so I haven't forgotten Pascal, but I'll get to him in a minute. So Wojciech and I, we work both at the University of Oslo in the same research group, and we work a lot with the Aurora. And here you see an image taken in northern Norway of the Aurora, and we try to understand not really where the aurora comes from, but how it behaves when it occurs, and those kinds of different things. And we also, as a group, we operate these auroral images, which are cameras that take pictures of the sky. You'll see some images that we deal with in a minute, and then we analyze them. And it's manual work, because you go through all the images and you look for interesting events. And so I thought, if we could automate this somehow using Hannes's expertise in machine learning and digital image processing, then that would be awesome. So we got together. But before I tell you what we then did, I'd like to introduce, I don't know how familiar you are with auroral images and where the aurora comes from, and so I thought I'd take a few minutes and introduce what we're really talking about. So here's a very famous picture. It shows the Dungy cycle. Let me get my virtual pointer going like this. So most of you, I guess, will know that there is such a thing as the solar wind. The upper atmosphere of the sun isn't stable, so it's blowing off into space. And it's not only the particles of the upper atmosphere that blow into space, it's also the magnetic field of the sun. And as this magnetic field reaches the Earth, here's the Earth has an internal magnetic field, and these two magnetic fields can couple in a process that we call magnetic reconnection. And that happens here on the day side, where the interplanetary magnetic field, as we call it, coming from the sun, couples with the terrestrial field, and then it's transported, the magnetic field is transported into what we call the magnetotail back here. And here we have another location where magnetic reconnection can occur. So the thing I want you to take away from this is that there's this thing called magnetic reconnection, which pumps energy into what we call the magnetosphere, this region around the Earth, which is filled with plasma, and it's dominated by the terrestrial magnetic field. And so it's the day-side reconnection that pumps the energy into the system, and then it's the night side energy, the night side reconnection that releases that energy, and that is really what causes the aurora on the night side. So really, when you talk about the aurora, it's the light that is produced by particles which are accelerated here at the reconnection site or along the way. They zoom down the field line, they hit the particles in the upper atmosphere of Earth, excite them, they start emitting light, and this is then what we see as the aurora. So have that in mind. And then what I wanted to introduce is Akasofu's Tippy Bucket. So Akasofu he's if you want, the godfather of the Substorm of the Aurora research. He was a postdoc in Alaska, I believe, and he wrote in the early 60s a very influential paper where he described an aurora process that we still deal with today, which we call the substorm. And to understand what the substorm is, I'm going to use his analogy of the Tippy Bucket. So I told you that the day-side reconnection is pumping, transporting energy into the tail, the night side, the area behind the Earth, if you like. The sun is to the left in this image. And then the energy is released by this night side reconnection, but it's not, they are decoupled. So it's not like as soon as you have day side reconnection, the night side reconnection initiates and produces this aurora. It's that the day side reconnection loads energy into the tail, and then at some point it's released. So you can think of it in this analogy. This is Akasofu's Tippy bucket. So his bucket is actually down here. So what you can think of is that you have the IMF, the interplanetary magnetic field, which couples to the day-side magnetic field of the Earth and then puts energy into what we call the magnetosphere. So in this case, it would be gravitational potential energy, and in the magnetosphere is magnetic energy, but you get the idea. And so we're pouring water into this reservoir, and it has two spouts. And one of them is what we call the directly driven component, because there's always a little bit of aurora going on. Okay, there's the input. So here are images taken from space. You're looking down on the North Pole of the Earth. The sun is illuminating the day side here. And then you see this part, which we call the auroral oval, which is this circular shape in which most of the aurora occurs. And you see, even during quiet times, you have aurora. You almost always see aurora if you just look hard enough. And so you have this directly driven component which comes out of one spout, and it constantly releases a little bit of energy from this big reservoir. And then the other energy seems to fill up this tippy bucket, which is called a tippy bucket because at some point when it's full, it tips over and releases all this energy explosively into the ionosphere ultimately. And so while this process on the day side is kind of a more or less steady process, the night side reconnection can be very explosive, and the magnetosphere is pretty quiet, and then suddenly it explodes. It pops. The bucket tips over. And the issue that we've been fighting with for a number of years now is when does the bucket tip? Because in this analogy, you would think, well, I can find out how big the bucket is, and I can find out how fast the water is pouring in, and then at some point, I know pretty much exactly when the bucket is going to tip. But that when that bucket is tipping is still open for debate, let's say. It's still a question that we haven't fully understood. So that I tell you this because there's different kinds of aurora. There's the aurora, and it expresses itself, if you want, in different shapes of the aurora and different dynamics of the aurora. So this directly driven component is quite steady. We usually see what we call an arc. What's my next image? Here you go. So this is the images that we deal with. And here you see the aurora in green, and it's what we call an arc. It's this elongated shape, which is east-west aligned usually. And it usually just sits there and is quiet, and maybe it flickers a little bit, but there's not much dynamics going on. This is, by the way, an image taken from Hornsund, which is on an island north of Norway, on Svalbard. Down here you have the field station. It's a Polish research station, and they have kindly allowed us to put our camera there. And you see a bit of the background and the other scientific equipment that they have there. This is light from the field station that they need to have turned on in case polar bears come. And so this is then what the a quiet aurora would look like. And this is what Substorm Aurora looks like. And so you see it's very, well, you don't see it's dynamic, but you can imagine this is much more dynamic. It's much more moving about. It's changing shape. It's changing the extent at which it illuminates the sky. And here's another image. And so what we would like to do, or let me start the other way. So previously, the analysis of these images has been very manual. So you go to your image collection and you click through them, through the thumbs and nails, and you kind of try to find these events and then try and understand what's going on. And that's very labor intensive work. And so we thought, well, can we not automate this with these new machine learning techniques that we all have heard about? Because the other thing that happens is that most of the auroral images that we take actually look like this. Because what happens is the aurora is roughly at 150 kilometers altitude or higher. And between that and us is weather. And so we have clouds, rain. You saw a little bit of that here, so you see that this area of the image is actually obscured by clouds. And so a lot of the work we do is also just weeding out these images that nobody can use, like this one or this one. There's actually snow here, so suddenly you can't even see the instrument here anymore because it's been snowing. And also the moon poses a problem. So this is not the sun, that's the moon. And it's bright enough to obscure the aurora in certain cases. So if you look very, very closely, you might see a hint of green here, but you can't really tell whether it's there or not and what it's doing because the moon is also in the sky polluting the image. Now the moon is obviously something we can deal with to some extent because we know where it's going to be at what night, and we can just automatically get rid of these images. But still, maybe you don't want to throw away the entire picture just because the moon is in it, because other parts of the picture might still be useful. And so this is then the kind of work that I'm going to present that we did with a lot of these images. So what we did is, I told you just all of this. So there's different shapes of aurora, and we want to distinguish between them automatically, whether they are what we call arcs, these elongated shapes here, whether it's diffuse, where you kind of have aurora, but it doesn't really have clear contours, or it's discrete, where you have clear contours, but it's not really arc-shaped, or whether it's the moon or there's just no aurora. That happens also, you just see the stars, or whether it's cloudy. And so what Hannes suggested to do is to not train a network. Your first instinct might be, well, let's just go ahead and train our own network and do all of this work by ourselves. But what he suggested is, no, let's not do that. Let's take one of these pre-trained networks that can detect container ships and daisies and panda bears and all those kind of things. And what we will do is that we will, as you might know, a neural network consists of two different parts. So you have the one part, which is the convolutional part, which is really a feature learning part, where the network learns to extract the features from the image that are important. And then based on these features, it takes a decision whether you are giving it a car or a truck or a daisy or panda bear. And so what Hannes suggested was to keep all of this from this pre-trained network and then start taking out the feature vector, which is this big vector which codifies the features that this part identified. And we run our auroral images through this pre-trained network, and it's trying to find panda bears or whatever, daisies. but it's before it's deciding what it's seeing, it has this feature vector on which it bases its decision. And so what we said is, okay, let's take the feature vector from our auroral images, use a different kind of classifier, which is in our case a ridge classifier, but it could be a support vector machine or any other algorithm that you might think is good. And then based on that, we do the prediction. So really, we just take the hard work other people did training this network on other images, and then we extract the feature vector and use that for our prediction. And you can see this is our confusion matrix from our first test run with this pre-trained network. It works quite well. Here's the part where Aurora is observed and Aurora is detected. You see there's some overlap. It's not always perfect, but certainly it's staying within the Aurora categories. It's seldom taking any of the discrete or diffuse Aurora and identifying it as the moon, for example, and vice versa. The other non-auroral features are also kind of staying to themselves and are rarely identified as Aurora. And what this allows you to do, potentially at least, is that there's millions, literally millions and millions of these auroral images from not just our network, but from many other networks, and that you could automatically classify with these pre-trained networks, and then have this time series, attach a label essentially to each image, and that would allow you to do large statistical studies, which you couldn't do on a manual basis. So you could, imagine having this large database with all the images, and you say, I want all the ARCI images on a Wednesday that occurred after Thanksgiving. And whether that makes sense or not, you would be able to do that. And if you were to do that by hand, it would be a very tedious process. So that's one of the things that we're looking into. The other thing is, and that's where Pascal comes in, who is a PhD student working with us, is that he's been digging a bit into what the network does and how well it performs. So one of the things you can do is, well, you can ask the network, give me those images which you are most certain about are arcs. And then it gives you these 50 or 49 images, and you can convince yourself that it's doing a good job. There's some arcs which are not aligned in the usual way, but we know they exist, and so we're not worried about those, and they all look very archy to us. And then you can also ask, so what are the worst images, saying that, or asking, well, the network still says it's an arc, but it's really not very confident about that decision. And you can see why it went wrong. So we're confident that the network is, although it's been trained on completely different data set, by looking at the feature vectors, we have a pretty good understanding that the network is actually looking at these auroral features. And in all of these images, you could argue, well, okay, maybe there is an arc here probably. And also, as a human having to do this classification, I would be uncertain how to classify this image as well. So it's okay, so to speak, for the network to be uncertain. And what Pascal also did is do this mapping of the feature vector. So the feature vector has 1,001 entries, and you can use this technique to map it onto 2 dimensions, which is shown here. So this is, I believe, over 500,000 images which were classified by this technique. And instead of showing the feature vector in a 1,001 dimensional space, we condense it down to 2. And you can see how the different classes kind of cluster, how this mapping does a pretty good job of separating these different features from each other, which again makes us confident that the network is actually doing a good job. Here's another. So what I'm showing here, or what Pascal is showing here, you may see a little red square here. So he's zooming in on this region, which is showing these points, which were all identified more or less as cloudy. And you can see that if you then pick a random selection of these images, it's cloudy. And if you zoom in on an image where most of them should be archy, or discrete, sorry, class 1 is discrete, then you see images that are mostly discrete. Some of them are arcy, but it's sometimes difficult to tell the difference between arc and discrete. So we're pretty happy with this. And what we're trying now, or what Pascal is trying now, and brings me to the end almost of my presentation, is that he's using this feature vector to predict magnetic signatures. So Aurora is associated with currents in the ionosphere, and we can measure these currents by their magnetic signature. You know, by Ampere's law, every current has a magnetic signature, and so by measuring the magnetic field perturbation, we know when there's a big like shown here in blue, a big perturbation in the magnetic field. Usually that means a lot of aurora. And so what Pascal is now trying to do is predict the magnetic field from these feature vectors. And the green is the prediction. And we're better than just predicting the mean. Let's put it that way. It's very early. We've only started this work. But this is some of the things that we intend to do, and not only predict magnetic signatures, but also in the end, maybe something like GPS scintillation. So you know maybe that the aurora also affects the signals coming from global positioning satellite system signals. Well, that was a lot of signals, but you know what I mean. They have to go through the aurora. They are disturbed. These signals are, and so we would like to understand how and when that happens, and maybe we can then build a machine that will predict the signal quality of GPS based on these feature vectors. The last thing that I would like to just throw out there, because we've been looking into that, is these images obviously have different areas. There's different, it's not just one type of aurora in the image. Just like if you have any image, there's probably different objects in them. And there's techniques, which are these region-based convolutional neural networks, that can identify different regions and classify them differently from each other. Instead of just labeling the entire image as maybe a bicycle, you say, well, this part is a bicycle and this part is a dog, and so on. And we're hoping that maybe in the future we will be able to then take an image like this and say, well, this part is what we call clear sky. Here we have some clouds, here's the arc, and here's the moon. And that would then also allow you to do a lot of these statistical studies much easier than doing it manually. And I'm sorry, I think I've talked longer than I should have, but this is my introduction of what we do here at the University of Oslo. So thank you very much for your attention, and I'll be happy to take some questions. Thank you.